Dzień dobry. Witamy Państwa w Centrum Nauki Kopernik. Bardzo nas cieszy to liczne przybycie. Ja nie będę dużo dzisiaj mówił, jestem tylko mistrzem ceremonii. W związku z tym mam prośbę bardzo ważną dla nas o wyciszenie bądź wyłączenie telefonów komórkowych. To na początek. I o parę słów powitania od dyrektora Centrum Nauki Kopernik, pana Roberta Firmhofera.
Mam ogromną przyjemność powitać Państwa dzisiaj w Centrum Nauki Kopernik przy tak niezwykłej okazji, jaką jest wykład Sir Rogera Penrose'a na temat, który, jak Państwo widzą, w dodatku jest ściśle związany z miejscem, w którym się spotykamy. I bardzo się cieszę z tak licznego przybycia. Mamy chyba po raz pierwszy nadkomplet w tej sali. Proszę Państwa, ja nie będę przedstawiał naszego gościa, uczyni to za chwilę pan profesor Marek Demiański, ale jak myślę wszyscy Państwo wiedzą, Sir Roger Penrose jest tą osobą, która stawia najbardziej fundamentalne pytania w kwestiach, które są najbardziej doniosłe, w tych, które dotyczą natury, początku i przyszłości wszechświata, ale także tego, w jaki sposób go poznajemy, naszej świadomości. Jesteśmy ogromnie wdzięczni, że możemy gościć dzisiaj Sir Rogera Penrose'a wśród nas. Sir, we are very pleased and honored and privileged that you are today with us. Thank you very much for accepting this invitation. Thank you.
My pleasure. Okay. Okay.
I chcę też podziękować za umożliwienie tego wykładu organizatorom bardzo ważnej konferencji, która odbywa się w tej chwili w Warszawie, konferencji 20GR i 10 Almado. Profesor Marek Demiański powie o tym kilka słów więcej i także wprowadzi krótko naszego gościa. Chcę tylko powiedzieć, że pan profesor Marek Demiański, wybitny polski kosmolog, fizyk relatywistyczny, wśród bardzo wielu afiliacji mogę chyba wymienić Instytut Fizyki Teoretycznej Uniwersytetu Warszawskiego. Panie profesorze, dziękuję bardzo.
Dzień dobry Państwu. Wczoraj skończyła się w Warszawie 20. Międzynarodowa Grawitacyjna Konferencja. To była wielka impreza, na którą przyjechało 850 naukowców z całego świata. Mieliśmy to szczęście, że wśród nas był również Sir Roger Penrose. Ta konferencja jest w pewnym sensie kontynuacją tradycji Warszawskiego Ośrodka Relatywistycznego. Pierwsza taka konferencja była zorganizowana w roku 1962 w Warszawie i w Jabłonnej. Właściwie trzeba by ją nazywać konferencją w Jabłonnie, dlatego że tylko jeden wykład odbywał się w Warszawie, ale to z powodów takich ceremonialnych. Różni ministrowie, prezesi różnych ważnych instytucji powinni to otworzyć, więc Jabłonna to było za daleko. A potem cała konferencja się przeniosła do Jabłonnej i mieliśmy to ogromne szczęście, że już w Jabłonnej był Sir Roger Penrose, jako, można powiedzieć, chłopaczek. Na tej konferencji przedstawił jedną z niezwykle ważnych i istotnych wizji o tym, jak wygląda płaska czasoprzestrzeń Minkowskiego. Jak można tą płaską czasoprzestrzeń Minkowskiego ścisnąć tak, żeby zobaczyć, jak wyglądają te punkty daleko w nieskończoności. I tą ideę rozwijał następnie przez wiele lat. Część z tego zobaczycie Państwo dzisiaj. To była jedna taki wielki wkład nowego spojrzenia na własności czasoprzestrzeni z czysto matematycznego punktu widzenia, można by powiedzieć. Następnie Roger Penrose był prekursorem używania spinorów ogólnej teorii względności. Wspólnie z naszym wspólnym znajomym Tedem Newmanem opracował formalizm, który się nazywa teraz formalizmem Newmana-Penrose'a i jest niezwykle efektywnym aparatem do badania asymptotycznych własności czasoprzestrzeni w różnych sytuacjach, a również do znajdowania nowych rozwiązań równania Einsteina. Następnie tą koncepcję spinorów uogólnił i w roku 1967 wprowadził no taką rewolucyjnie nową koncepcję, która się nazywa twistorami. I jak Państwo zobaczycie, twistory będą się pojawiały dzisiaj również na kolorowych obrazkach profesora Penrose'a. Oczywiście profesor Penrose z powodu tych... Aha, jeszcze jedną rzecz warto powiedzieć, że oprócz tych takich bardzo matematycznych koncepcji, Roger Penrose, korzystając z bardzo zaawansowanej matematyki, udowodnił na przykład, że każdy proces grawitacyjnego zapadania masywnej gwiazdy prowadzi do powstania czarnej dziury, a w samym centrum czarnej dziury powinien powstać obiekt, który będzie miał niezwykłej gęstości. Ten obiekt teraz nazywamy osobliwością. Pokazał również, że korzystając z tego, co widzimy teraz, co widzą astronomowie, co jesteśmy w stanie zmierzyć, wszechświat powstał skończony czas temu. Wiemy, że wszechświat jest dość stary, licząc w nasz wiek w porównaniu z wiekiem wszechświata, ma w tej chwili 13,7 miliarda lat. Proszę bardzo, proszę wejść. Okay. Otóż dzisiaj również profesor Penrose skorzysta z tych twierdzeń. Oczywiście te ogromne osiągnięcia, te ogromne zasługi dla nauki zaowocowały serią różnych wspaniałych nagród, medali i tak dalej. Ja naprawdę nie mam czasu, żeby wymieniać wszystkie. Chciałbym tylko powiedzieć, że Sir Roger Penrose wspólnie ze Stephenem Hawkingiem dostali Nagrodę Wolfa. To jest jedna z najważniejszych nagród w dziedzinie matematyki i fizyki na świecie. Profesor Penrose jest również doktorem honoris causa Uniwersytetu Warszawskiego. Także wśród tych licznych zasług, wśród licznych odznaczeń jest również nasz hołd Uniwersytetu Warszawskiego. Proszę Państwa, macie Państwo niezwykłą okazję zobaczyć, posłuchać i przekonać się. Niezwykły umysł, niezwykła wiedza, niezwykła fantazja. Za chwilę pan profesor Penrose opowie Państwu o nowej kosmologicznej ewolucji, rewolucji, chwileczkę, nie będziemy zaraz robić rewolucji. Proszę Państwa, chodzi o to, że to nowe spojrzenie na ewolucję wszechświata prowadzi do rewolucyjnego wniosku, że zasadę kopernikańską można rozciągnąć niewyobrażalnie daleko. No ale o tym powie Państwu już profesor Penrose. Także witamy Sir Rogera Penrose'a.
Dziękujemy bardzo za podsycenie naszej ciekawości. Profesor Demiański będzie dla Państwa tłumaczył wykład na język polski. Teraz można założyć słuchawki. Znajdą Państwo po jednej stronie guziki związane z głośnością oraz z przełączeniem kanału. Kanały są dwa. Jeden jest oryginalny, drugi z tłumaczeniem. Mam nadzieję, że nie sprawi to nikomu problemu. Po wykładzie planujemy dyskusję. Będzie okazja, żeby zadać profesorowi Penrose'owi pytania i uzyskać odpowiedzi. Jeszcze chwila cierpliwości i czasu. Dyskusja będzie również tłumaczona nie przez słuchawki. Będzie trochę szybciej. Jeśli będą Państwo odczuwali niedosyt wiedzy po dzisiejszym wykładzie, można zaopatrzyć się w jedną z dwóch książek Sir Rogera Penrose'a, które można kupić zaraz przy wyjściu z sali konferencyjnej. i możemy zaczynać. Sir, please. We can start.
Okay, can start. Thank you. Actually, I should bring this with me. Well, thank you very much. It's a great pleasure for me to be back in Warsaw and back in Poland, where so many great mathematicians, and particularly Copernicus, who I want to pay my respects to today. Of course, we all know he put forward the view that the Earth was not really the center of the universe, and that we had to think of the Earth as just another planet around the sun. And so we had a view which was less central to our own existence. I mean, our existence was somehow not central to the universe. Now, when I was becoming interested in cosmology as a young graduate student, it was at a time, particularly in Cambridge, where I did my graduate studies, when the theory known as the steady state theory was being promoted, particularly by Bondi and Gold and Hoyle, who were all at Cambridge at the time. In the steady state theory, it was in a sense more Copernican than the theory where you had a big bang and the universe expanded. And the idea in the steady state theory was that the expanding universe, there was new material created all the time, and so the universe more or less stayed the same, even though it was expanding. It was a clever theory, but when observations became more evident that that there was an expansion of the universe which was not a steady state, and that there was evidence for the existence of a Big Bang, then the steady state really became obsolete at that time. However, there was this idea that somehow not just your spatial location was not really very special, that there was something not so special about the Earth, and then we learnt there was something not so special about the Sun. There was only one star among many in the galaxy, and not so much special about the Milky Way galaxy, because there are many other galaxies. And so somehow our location spatially in the universe was not so particular, apart from having a planet that was rather comfortable to live in, and that was why we were here, because we have to have a comfortable planet to live in in order to exist. Now, the steady state model extended that idea to saying there was nothing special about the time, and that a later time and an earlier time were more or less just the same. That idea is not accepted anymore. However, I want to tell you about a scheme which I've been working with for several years now, which in some sense brings back the idea of a steady state. It's not the same as the steady state universe, and I want to describe that in more detail, but it does have that kind of Copernican feeling about it, that the present time, in a certain sense, is just the same as other times. But I'll have to explain what that sense is. So I should say, by the way, that unfortunately all my transparencies, as we noticed, may fit better that way around, but they are designed for what's called the portrait orientation rather than the landscape orientation. So I shall have to keep sliding things up and down so you can see them. And also, I think you may notice, I don't think you can tell from that, but you'll be able to tell there's a sort of squashing too. So you have to imagine, in your imagination, you have to squash the screen, stretch it this way, and also imagine that it goes up and down. We'll see how it works anyway. So the first one, for example, I want to talk about the earliest cosmological models after Einstein introduced his general theory of relativity. And these were really, there were several, but Friedman, I think, was the first. In 1922, he suggested various models. These were solutions of the Einstein equations, which were very Copernican with regard to the space, but time was not Copernican. That is to say, most spatial locations were sort of on an equal footing with each other, whereas the time evolved. Now, I shall have in my diagrams time going upwards. Of course, it would be easier to do it now. I could show the time that way, but never mind. This is the usual convention that we use in relativity theory, that the time is represented as going up the picture. And we have three models here, those three being distinguished because of their spatial geometry being either Euclidean, as is represented here. K0 represents the curvature being 0. You have to think of that as a sphere. It looks a little squashed, but try to stretch it out. So here, this is the positively curved space, and this is the negatively curved space. And those three possible spatial geometries, they're completely uniform, so it doesn't matter where you are. This one, you have to get the idea, you see, because if you were one of these angels or devils, whichever you prefer, and you lived in the middle here, you would be indistinguishable from those ones that live right out here. So you have to imagine that you stretch out the universe over here, and it would look just the same as here. So as far as the creatures who live in this universe are concerned, it's completely uniform. It doesn't matter where they live. We'll come back to that later. This one has a particular role in what I want to say. I should say I don't mind, for the purposes of my talk, whether the universe is spatially like a Euclidean space, whether it is positively curved up like a sphere, or whether it is this open universe with the negative curvature. Doesn't play any particular role in what I want to say. Nevertheless, I can show you what the three Friedman models, although I believe he only did these two as a matter of fact, but that's just a historical point. He would have known about that one. We have these three different possibilities depending on the spatially closed up geometry, which would be that one, the Euclidean one, which is that one, or the negatively curved universe, which is that one. And you see that the temporal evolution in some sense reflects the spatial one. That is, the closed up, spatially closed up universe has a finite time. They all start with a big bang, and the universe starts to expand, and these ones it continues to expand. This one keeps on going. This one sort of slows down in its expansion. This one reaches a maximum and then collapses down to what's referred to as a big crunch. So those were the models that were introduced very early on in the history of Einstein's general theory of relativity. However, in recent years, in 1998 or so, it was found that these models aren't really the right ones, apparently, that there is an accelerated expansion which has started to take over. And the pictures, all of them, are rather like this. Well, you can get the whole thing, unfortunately, but I should explain why the back looks a little unclear. That's because I'm not trying to say the universe is closed or open. It doesn't matter for what I want to say. But we do have a big bang, the expansion keeps on going for a while, and then it starts to accelerate. And this accelerated expansion, when people were looking at very distant supernova stars, they found that there was this accelerated expansion and were somewhat surprised by it. I don't quite know why they were that surprised, because in all the cosmology books I know, there was discussion of this cosmological constant. It was a quantity called lambda, which is a constant number. In these versions, that lambda is always 0. Einstein then introduced the lambda which might not be 0 for, in fact, the wrong reason, because he wanted to have a universe that was static, that wasn't expanding or contracting, and in order to have that universe, he needed to introduce this lambda. And then when the universe was convincingly shown to be expanding, he had to retract, and he's said to have said that this was his greatest mistake, introducing this lambda term. However, even Einstein's mistakes turn out sometimes to be true. And in this case, it did seem to be the case that the universe is doing what would be consistent with a lambda which is positive, not 0, but greater than 0. And all of those models, whether they're closed or flat or what, as far as the spatial geometry is concerned, will undergo this exponential expansion. If you want to know where we are in this universe, we're somewhere around about here, where we're beginning to see this expansion. And, we'll come back to what that thing's going to do eventually, shortly. But for the moment, let me talk about something else. Those of you who've been looking at cosmology books and so on, or know about cosmology, will have heard of this thing called inflation, which is supposed to have taken place right at the beginning. Now, I have not drawn it in this picture for two reasons. One is, well, maybe I have drawn it. You just wouldn't know, because inflation was there. If it were there, it would be tucked right into that corner, and you just wouldn't see it to scale in this picture. However, there's another reason why I haven't drawn it, and that is I don't really believe it. And if you don't believe it, you have to have some other explanation. But before, let me try and see what's going on there, and I'll bring my magnifying glass along. And what does that see? Well, that magnifying glass sees something like this. I should point out is the handle to the magnifying glass, because sometimes people are confused by what part of the universe that is representing. But that's the magnifying glass handle. And what you see is another exponential expansion, which apparently, so the story goes, took place in the very early universe. So it's tucked right in there. With the magnifying glass, you see it. And you notice that there is a very great similarity between the alleged inflation expansion and the ultimate expansion that is supposed to be going to take place. Now, when I say I don't believe in inflation, in a certain sense I do. As I say, inflation explains certain features of the universe. Some of these features I don't think it really does explain, and when it was first introduced, for various reasons, I didn't think those reasons were very good. However, there are certain reasons about the behavior of the microwave background radiation. There's radiation coming in, electromagnetic radiation, or if you like, very low wavelength light coming in from all directions, and this radiation tells us a lot about the nature of the very early universe, and in order to explain certain features of that, inflation has seemed to be the only way to explain it. What you need is some sort of exponential expansion like this out here, but going on in the middle, right near the Big Bang. Now what I'm saying here is that there was no inflation, except that in a sense there was, but it was not after the Big Bang, it was in a sense before the Big Bang. Now this idea is not original with me. There's a famous Italian physicist called Veneziano who'd introduced, for quite different reasons, the possibility of inflation that was before the Big Bang. Now, how do you make sense of such a strange idea? Well, let me try to tell you how to make sense of it. What you do, I want to do, first of all, just a couple of mathematical tricks. Two mathematical tricks. There, you have to see that now. One of them is to squash infinity down to get a smooth future boundary. You see, this is what this picture does. Here we have a universe. This is just space now, not time. But in this universe, infinity has been squashed down to make a finite boundary. And this is what's called a conformal squashing down, a conformal transformation. Unfortunately, what you see is not a conformal transformation, because that should look like a circle, and I'm afraid it doesn't quite. But you have to, in your mind, squash it inwards so that it does look like a circle, and then that is what's called a conformal map. So if you could see, for example, the eyes of the devils here, no matter how close to the edge you get, they would be the same shape. They would, however, be much smaller represented here, but you don't care about big and small. The point about conformal geometry is that it's angles and little shapes that are what the geometry is concerned with, not distances. Big distances and little distances are equivalent, but you could have a big triangle or a little triangle, and if the angles agreed, those triangles would be considered to be, from the point of view of conformal geometry, they would be considered to be the same. So we have to get used to that idea for things I want to say later. But what we're trying to do here is squash infinity down in this conformal way, just as in this picture here. Infinity is being squashed down, and you can make it to a nice smooth boundary, like in that other picture. There's a converse trick, which is this. You stretch out the Big Bang, to get a smooth initial boundary. Now you see that picture doesn't sort of fit very well here, so let me take another one. I've just drawn the universe smaller. Well, you see that's a conformal transformation already, just to make it look smaller. But I've squashed infinity, that's the very remote history, the utterly remote part of this future, and I squash it down to be a completely finite boundary. And conversely stretch out the Big Bang to make it into another finite boundary. That's, as I say, just mathematical tricks. Squashing down infinity and stretching out the Big Bang. Now, I should say that these tricks have a very different logical status. According to some very general results, mainly due to Helmut Friedrich, that when you have a positive cosmological constant, lambda, with this accelerated expansion, you can squash it down so that it forms a surface which looks like a kind of moment of time. You see, the time stops fairly uniformly all over the whole thing, and this is what we call a space-like surface here. This works under very general circumstances, so this is a trick which you can just use to describe universes. That's rather handy, model universes. The expanding out of the Big Bang is, on the other hand, an extremely strong restriction, and it expresses gravitational degrees of freedom. This is an idea which was developed by my colleague Paul Todd, and I want to say a lot more about that shortly. So we have the two tricks, one of them that you can more or less do whenever you want to, or whenever it's in the remote future, of course, for the model, or the other one, which is a huge restriction. So bear that in mind, but I want to tell you now what's outrageous. There's nothing outrageous that I've done here. What's outrageous about it? Well, I'm going to say that in a certain sense, this is real in the sense that what we have to picture the universe as like is this continuing succession, that the remote future of, say, that's our, I'm going to call this our eon. There was, I say, an eon prior to ours. There was another eon which is going to come after ours. And if you want to see how they join together, you have to do this conformal trick. I squash this one's infinity down, stretch out the next one's Big Bang, and they join smoothly together. That's the idea. A rather ridiculous idea, if you like, but never mind. That's what we're going to explore. And so this is the picture. Now, it's not the first time that in cosmology people have tried to have universe models where you have continuation. I'm trying to find where this is. Perhaps I may have done that later on. Yeah. I think things have got slightly out of order. I'll come back to that. I'm going to say why I've done the trick this way. But before saying that, let me also say, where are we in the picture? Well, we're round about here. About there, actually. So I can do it here. We're about there. So this means, you see, you might think we're a long way to go in the universe because there's all that infinite expansion. But in a certain sense, most of the interesting things have happened in the universe, and it gets pretty boring out there. And the Big Bang, and before us, there's a lot of interesting things happening. I want to quantify that a little better later on. But this is more or less where we are in the picture. So it's somewhere in the middle here, but comes to a point about there. So if you are prepared to accept something like this, what's Copernican about this is we're not in any particular one of these eons, and they're all a bit like each other. I think I'm going to have to wait till I get to that on my transparencies. I believe I've ordered them in a way which I didn't quite intend. Perhaps I can find it. 1 minute. No, I don't know where. Never mind. When I see it, I'll talk about it. Okay, so that is the general idea, and I want to try and explain certain things as to why I'm suggesting such a proposal. Now, the first point to think of here is this microwave background, which I referred to a short while ago. The microwave background being this radiation coming to us from all directions. And I want to think of that microwave background in the context of a very fundamental principle of physics. This very fundamental principle of physics is what's referred to as the second law of thermodynamics. Now, what is the second law of thermodynamics? The second law of thermodynamics is a statement that things get random and more random as time goes on. More precisely, you tend to talk about this in terms of a quantity called entropy, and entropy is a measure of randomness. We can be more precise about that, but that will do for the time being. So we have a picture of the universe where the entropy or the randomness is increasing all the time. Now, if the randomness in the universe is increasing all the time, another way of saying exactly the same thing, and let me go back, I think, to my original universe picture here. See, entropy is increasing, getting more and more random out there. Another way of saying the same thing is if you go back in time, things are getting less and less random, more and more organized. And that's just the second law all over again. And whereas it seemed kind of natural that things could get more disorganized with time, if you don't do anything about it, well, it just things get more disorganized. But what about the great organization that must be present at the Big Bang? You see, it's just, as I say, saying the second law all over again. But one of these curious things about the Big Bang is already a feature of the microwave background, which is one of its most striking features. And I have here a picture which illustrates what I'm saying. See, this is electromagnetic radiation coming from all directions. It corresponds to a temperature which is about 2.7 degrees above absolute zero. So it's very, very cold. It's sometimes referred to as the flash of the Big Bang, but since the expansion of the universe has cooled it all down, by the time it gets to us, it's very, very cold. But it was at one time extremely hot. And this is what's called, as I say, the cosmic microwave background, or CMB. Now, two features about this are going to be important in what I say. One of them is this curve here. Now, what is that curve? Well, it's what's called the Planck radiation curve, and I've plotted horizontally the frequency of the radiation. It's a mixture of different frequencies, and the intensity for each frequency. So the intensity is up this way, and the frequencies are going this way. And what we see is, well, this solid curve is a theoretical curve, but what you actually see are these error bars. Now, this is an old slide, and it's probably much better even than in this picture, but you have to notice that even though these error bars look quite big here, they're exaggerated by a factor of 500, so even the worst one down here, if you divide that by 500, it's really hugging this curve to within the thickness of the incline in the picture. So you have an extremely good concordance between the observation of the microwave background and this curve. Now, what is this curve? It's the Planck black body spectrum. Don't worry about what it means in detail. It's in fact the thing that started quantum mechanics up at the beginning of the 20th century. But the point here is it represents thermal equilibrium. Now, what is thermal equilibrium? Thermal equilibrium means maximum entropy. Now, you may notice that there's a certain curious, almost paradox here. You go back in time, and the universe should be getting more and more special. It should be getting lower and lower entropy. And finally, when you get to the Big Bang, you see something which is at a maximum entropy. It's thermal equilibrium. Now, that would be nonsense if, well, you might say, well, maybe what the answer is that the universe was expanding and somehow did the best it could. Well, that's not the answer. I should just say, don't worry about that, because it's not the answer. The answer is something quite different. It was very special. The Big Bang was indeed extraordinarily special, but you don't see it here, because what you're seeing here is basically photons, or light, coming from matter. And the Planck body, the Planck black body spectrum has to do with matter and radiation in equilibrium, maximum entropy, most random you can have, with light and matter just bouncing off each other in a completely random way. It's not seeing something else, though. And something else is the important thing that I want to address here. And we can address that question if we think of the other feature, most blatant feature of the microwave background, not just this curve, but the other thing is that whatever direction you look in, the radiation is coming at us from all directions, whatever direction you look in, you see almost exactly the same temperature. Now, that tells us that the universe was extremely uniform in the early stages. And extremely uniform, well, you might say that also is consistent with maximum entropy. And that would have been the case had we had a model like something like this. Here's the second law of thermodynamics telling us entropy increases with time, disorder increases, roughly speaking. And one nice illustration of that, you can think of a gas in a box, and if initially you tuck it in one corner with some compartments here, remove the compartment, the walls, and the gas spreads out. So you see the entropy is going up and with time, and the gas spreads itself out uniformly over the box. So you see, uniform distribution means high entropy. Well, again, we haven't solved the problem, because we see a uniform distribution, high entropy, we see the Planck curve, high entropy. Where's the low entropy? Well, there's been something very important left out of this picture, and that is gravity. Now, I want to improve my picture here by bringing gravity in. Well, actually, I'm going to change the picture a bit. So we're thinking not now of molecules of a gas, but we're thinking of stars, maybe in a sort of galactic scale box, and stars running around. Now, they're attracting each other gravitationally, so there will be a tendency for them to clump together. And you'll notice that this clumping is the opposite of what's happening here. The entropy is still increasing all the time, but the picture looks different. You see, without the clumping, you have a low entropy state now, whereas here the high entropy state is the uniform state. And what we seem to see in the early universe is a uniform distribution, which is the kind of these two parts of my picture here, combination of this and this, where you do have uniformity. Now, this is high entropy with regard to the material contents of the universe, but with regard to gravity, it's low entropy. And there is this potential for things to clump, and the entropy goes up as the gravity starts to take effect. And indeed, this is crucial to our existence here on this planet. This is what we live off, if you like. Well, what do you say? How are you going to say? What does life depend on the planet? Well, you see, energy we get from the sun. That's the usual thing people say. The sun is out there, and it gives us energy. Well, I want to say that that's not really quite the right way of looking at it, because, well, you see, here is the sun out there, and here's us with all these things going on. The thing is that we get about the same amount of energy from the sun as we throw back again into the dark sky. So we don't gain energy from the sun. If we did, the Earth would simply get hotter. Well, it is getting hotter and hotter from global warming, but this is a tiny effect by comparison of what's going on day after day, that the sun shines on the Earth, gives energy to the Earth, but that energy goes way back out into space because the dark sky is cold, the sun is hot, and it's this imbalance between the hot sun and the dark sky which gives us the things we want. Well, more explicitly, the photons from the sun the sun being hot means these photons are of higher frequency. They're sort of yellow light photons on the whole, and because of Max Planck's famous formula, E equals h nu, that tells us that the energy is proportional to the frequency, and the little bundles of energy that come to us in the form of photons, they're each individually more energetic than the ones that go back out into space. So you need many, many more photons to go back out into space, much fewer coming in. So the energy is carried in little parcels of big energy and go away in lots and lots of parcels of little energy. And you can look at it and understand what this means in terms of entropy. This is the small entropy here, very organized, and this is the big entropy here with many, many degrees of freedom. All the energy is spread over many degrees of freedom. Okay, and it's the plants that cleverly make use of these high-energy photons to build up their substance, and then animals eat plants, we eat animals and plants, and that's how we do it. If the sky were completely uniform, all the same temperature, it would be useless. It's only useful because of this imbalance between the hot spot, which is the sun, and the cold sky. So that's absolutely crucial. Now, why is the sun a hot spot and a dark sky? Well, the main point to think about is, why is the sun there at all anyway? I mean, there are all sorts of complicated things going on, nuclear forces and so on, but the key point which drives everything is the fact that the sun is there. And why is it there? Because of gravity. It clumps from previously uniformly distribution of material, and stars were created in that way. And so that was the taking up of the gravitational degrees of freedom, which were potentially there, and by clumping, you get the kind of useful energy, the low entropy energy that we live off. So it is gravity which is the crucial thing. Without gravity, there wouldn't be stars, and we wouldn't be here. So this is a crucial point. Okay, so that's the main feature that I want to say, which tells us how you can square the second law of thermodynamics with the thermal spectrum here. It's just the matter and light which was thermalized, was maximum entropy. The gravity was far from it. It was just the opposite. Now, I think at this point, let me go a little further and address the question of the black hole here I mentioned at the end. You see, matter can just clump into stars, and that's certainly effective, taking up the degrees of freedom which were sort of waiting to be used in the early universe. But the extreme situation where entropy really goes shooting up is in this thing called a black hole. Now, we've heard a lot about black holes in recent years, and we know that our own galaxy apparently has a huge black hole in its center. Apparently it's not so long before it swallows some gas cloud out there, and cosmologists are getting very excited about what will happen when it swallows it. Well, perhaps not quite yet, but not too long from now that will happen. Now, what is a black hole? I should try and explain about black holes. And as I like to do, and I showed you right from the beginning, I like to draw these space-time pictures. So let me draw you a space-time picture of a collapse to a black hole. Let's start at the collapse here. We have some material, some star which got a little bit too big for the energy and the pressures and things. It couldn't hold itself apart. It won't happen to our sun, fortunately. I don't know if that matters too much for us, but nevertheless, the sun will not form a black hole. But if you started with a star which was 10 or much more times the mass of the sun, then there will come a stage in its life where it collapses and produces this thing called a black hole. Now, in order to understand this picture, this is the history, time going up this way, you really need to know what these things are. Those are the light cones or the null cones, and they are crucial to what I want to say. So let me just explain them a little bit. You think of the space-time as a four-dimensional space. Well, that's hard to imagine. Let's think of it as a three-dimensional space. That'll do for most things I want to say. And this picture is trying to represent the three-dimensional space, representing in one fewer dimension, a black hole forming. But the key point are these cones. Now, what are the cones? These cones, light cones or null cones, you have to think of them as sort of painted on the space-time. At any point, there is one of these cones. And what it's telling you is how light behaves. So if you had a flash of light there, its history would spread out over this cone. Time is going up the picture again, so it starts as a flash and then it spreads itself out. And here I've tried to illustrate in the full number of dimensions. Flash there, and it's getting bigger and bigger. Again, you have to think of I keep calling this 45 degrees. When you look at it, it doesn't look like 45 degrees, but never mind. That's just the squashing. I suppose I could do it like that. That doesn't work. Okay. So you have to think your space-time has these things painted on it all over the place. There's also the pass cone, which tells you where a flash that were to converge on that point, it would have to have a history which is like this cone coming inwards. But you just think that at every point there is conceptually one of these cones, and that gives you most of the structure of the space-time. And physically what it does, well, you see light would be represented, its world line of a photon would be a line which is always tangential to the cones. A massive particle would have a world line which is always within the cones. And so that's saying it can't go faster than light because it has to be within the cones. And special relativity, that's where there's no gravity. General relativity is where gravity influences these cones and tilts them around in various ways. But the rules are the same. The photon has a world line or history which is along the cones, a material particle within the cones. And so in the case of a black hole, you really do get some serious distortion of these light cones, and you find in particular this thing called the event horizon, where if you were unfortunate enough to find yourself in this region, there's no way you could get out. But you see, because if you try and draw your world line getting out, you find it would have to violate the rules I just said. But the world lines are always within the cones, so things can fall in this way or this way, but they can't get out. So that's bad news if you've made the mistake of falling into one of these things. The other reason it's bad news is there's this nasty thing in the middle referred to as a singularity. That really means that the geometry of the space-time goes haywire, curvatures become infinite, densities become infinite. And in fact, we had some singularities before, which I didn't comment on particularly. The Big Bang is another example of a singularity. And these universe models, these three of them all have Big Bangs. This one also has a future one, which is the Big Crunch, as it's sometimes called. But here we see the thing in the black hole, a more local situation where in center or somewhere in the middle, it doesn't have to be the center, it's maybe some complicated thing in the middle, which is a singularity again. So that's the picture that I was showing you before of the universe, the history of the universe. I think I need to improve a little bit. First of all, I have to find it. There we are. There's our picture of the universe, the history of it. And now I'm going to put in a few black hole singularities. Now, often when the early days of studying these things, people used to say, well, aren't they? They're just sort of the same. You have the black hole and the singularity and the black hole singularity, and you have the singularity in the Big Bang, and they're sort of the same, except one's in the future and the other's in the past. Well, in a certain sense, that's true, but there's a key thing here which is very different. And this has to do with the second law of thermodynamics. The Big Bang was a very special, very, very organized singularity which had low entropy, in which the gravitational degrees of freedom, whatever that means, were very, very low, whereas they're very, very high in the black hole singularity. So we've got low entropy here, and it evolves to high entropy in the black hole singularities. So you see the sort of extremes of the entropy occurring in this picture. In the future, the black hole singularities; in the past, the Big Bang singularity. And in fact, you see, one of the reasons that people introduced inflation in the early days was they wanted to explain why the universe was so uniform. And they thought if you start with a very complicated initial singularity, and then somehow you have this inflation which stretches everything out, it will then be all nice and flat, or pretty flat. Now, this argument really is wrong, and that's one of the reasons I worried about inflation when I first heard about it. Why is it wrong? Well, I'm going to imagine that the universe was collapsing. Now, the universe might be collapsing in this very smooth way, where I haven't put any of the irregularities into the picture. Now, of course, the universe we have will have bits of irregularities where things start to produce stars and planets and even black holes. But that all represents an increase of entropy. But if we had a collapsing universe in which there was still a second law of thermodynamics, well, then these irregularities will build up and build up and build up and become black holes, and these will congeal and make one absolutely horrendous mess in the end. So the picture is much more like this. Those are the congealing black holes, and you just get one incredible mess at the end. Now, the thing about the second law of thermodynamics is it is an additional thing which you have to you add to laws which are already symmetrical in time. So Newton's laws, for instance, are all, if you run the clock backwards, they work just as well as forwards, and that applies to all these laws. In the laws that govern inflation, that would be true too. There's a thing called the inflaton field that would work backwards as well, just as forwards. So all these things are reversible in time. So if this were the kind of thing that would happen in a collapsing universe, why didn't it happen in an expanding universe? That would be a far, far, far more likely thing. That's an extremely special situation. This would be the more probable kind of universe. But it would have a high entropy start. It wouldn't be anything like the universe we live in. It wouldn't be any use to us at all. But why wasn't it like that? Now I want to sort of try, yes, now I can find one of the things I was looking for right early on, so let me talk about it. You see, when people refer to universes where you might have had a pre-universe to this thing, and that's what I was trying to talk about, and people discuss such things right from early on. And they might say, well, the Big Bang might have been something result of a collapsing universe. And this is the kind of picture that people would produce. It would work for any of them. You could have this flat, spatially flat or spatially hyperbolic case. Or you could have the closed universe, which would produce what people used to refer to as the oscillating model. And so here you would have this thing bouncing in and out all the time, and that is an exact solution of the Friedman cosmology, but it has to bounce through the singularity, and people would worry about bouncing through a singularity, but apart from that, it seemed like a plausible model. Now, why have I not done that, you see? In my picture, I say, no, it's not a collapsing universe. It's got to be an expanding one, which somehow becomes the Big Bang of the next one. I'll have to explain how that works a bit more later, but it's not this picture. Now, of course, the reason, from what I've been telling you, that one of the big reasons I don't like this picture is that you've got to join two things which just don't fit. You see, basically, in your collapsing universe, as I said, you've got a great mess. In your expanding universe, you get something which isn't a mess at all, and you've got to try and fit that onto that, and they just don't fit. For the real physical reason, if you like, this is an enormously high entropy, and this is a very, very low entropy. And how are you going to get rid of all these degrees of freedom? It just doesn't make any sense. Well, let's think about this more now. First of all, let's forget about the physics, and let's try and do the geometry. We want to say, what is the nature of that Big Bang? Can we understand what it means to say it's nice and smooth? Well, for many years, I introduced a thing that I called the Weyl curvature hypothesis, and I'm not going to tell you what that means, because I'd have to tell you what the Weyl curvature was, and that's a tensor thing, and these are things you need to know the right mathematics for. Nevertheless, it didn't stop me proposing that idea, but it's nice that Paul Todd has a better way of saying it. Let me just try and address this huge constraint due to the suppression of gravitational degrees of freedom. In fact, you can estimate how much that precision is, and it's really extraordinary. And the estimate comes from the Bekenstein-Hawking formula for the entropy of a black hole. So the entropy in the universe now is absolutely almost entirely in black holes. Everything else is a totally trivial addition to it. The black hole that we have in the center of our galaxy, if you have similar ones in other galaxies, and yes, you've got even bigger ones in many galaxies, that is a huge contribution to the total entropy and swamps everything else. Now, using that formula, the Bekenstein-Hawking formula, you can estimate what the entropy in a collapsing universe would get to. You see, what have we got here? We've got all these black holes congealing into a mess. They get bigger and bigger and bigger, and you can make a sort of estimate. It's really what would have been the black hole if you produced all the matter in the observable universe, if you like, squash that all together into a black hole. How much entropy is there in that? Well, you have to think of a figure like 10 to the power 124. That is to say 124 zeros. Now the entropy, it turns out, is a logarithm of the number of degrees of freedom, roughly speaking. And so that means that when you think about it, that the improbability of the universe being like this as opposed to like this is something like 1 part in 10 to the power 124. That's an absolutely absurd number. But that is the specialness of the universe. And I've got it written down here. I used to say 123 up. It doesn't really make any difference. It completely swamps the 124 is ridiculously larger than 123 there. But for the purposes of argument, it makes no difference. For those of you who know about these things, the 4 is only there because I want to include the dark matter, which was not so accepted at a time when these numbers were talked about earlier. I got the original figure from Don Page, I should mention. But you see, we have this enormous constraint, and this is something you've got to explain. It's not something that's going to come about through inflation or something. Inflation doesn't do anything for it. It makes the number worse, actually. Now, you see, the Weyl curvature, as I say, it's somewhat awkward condition to stay in a precise way mathematically for all sorts of reasons. But Paul Todd's way of doing it is very neat. He has a very elegant mathematical proposal. Well, you see, I've removed it here from this slide because I don't want to tell you quite too soon. I'll come to that shortly. But before talking about that, let's think about the other end of the world. That is to say, the remote future. And in the remote future, what's it going to be like? Well, we get these black holes form. They swallow lots and lots of material. Not everything. They don't swallow everything, but they sit there. The universe expands, and it gets colder and colder. And, well, let me say one thing about black holes. They also, according to Hawking, have a temperature. You see, here I have a picture of a black hole, and it's doing what Hawking says. It has a temperature. Now, if it has a temperature, you might ask, what is that temperature? Well, big ones are colder than little ones. So if you want to know what the hottest black hole is, you better think about the smallest ones. Well, the smallest ones are a few times the mass of the sun. And what would the temperature be there? Well, to get some idea of that, think about the coldest temperature that has ever been produced artificially on the Earth, and you're in the right sort of ballpark. So they're not really very hot. Very cold, in fact. And the big ones are much, much colder. So you might say, why are we worrying about this anyway then? It's a totally trivial effect. Well, you see, if you're worrying about the remote future of the universe is going to be expanding and expanding and expanding, and this microwave background radiation, for example, will get colder and colder and colder and colder, and the universe will get so cold that it's not even as hot as the coldest black holes around. How long will they last? They radiate away. These black holes will then be the hottest things around, and so they will radiate energy to the outside world. And as that happens, they shrink away and get smaller, and finally disappear with a pop. Well, I've called it a pop because it's not, by sort of astrophysical standards, it's not much of an explosion. So, okay, that's what they do. How long does that take? Well, for the biggest black holes, think of something like a googol years. What's a googol? Well, it's not a very scientific term. It means 10 to the power 100, 1, 0, 0, 0, 0, 0, 100 zeros. That's a googol. Now, googol years is roughly the kind of time you have to wait for the biggest of these black holes finally to go off with a pop. Okay, well, that's what they seem to be. We're being told that's what they do. And so now my picture has to be modified by putting all the pops in. So I put them in. It's not to scale now. It's way up here somewhere. But don't worry about that. And I've marked here what happens after they've all gone pop. Well, that's what I call the very boring era. It's pretty boring already down here when the most exciting thing around is to wait for a black hole to go off pop. And you've got to wait for something like a googol years, and then it goes off pop. Well, I never thought that was terribly exciting, but that's really exciting compared with what happens afterwards. It's the very boring era. Now, I was thinking about this at one stage and thinking, is that really the fate of our universe? Well, that's what we're told now, you see. It's going to be this very boring, very cold, nothing happening universe. And I was sitting around being rather depressed by this thought, and then it occurred to me, who's going to be around to be bored by this universe? Well, not us. The main things that will be around to be bored will be photons. And it's very hard to bore a photon. It's hard to bore a photon for two reasons. One is it probably doesn't have any experiences, so that's fine. But the other reason is really what I want to talk about. There's another reason why it's hard to bore a photon. And that is because a photon doesn't feel the passage of time. Now, I've been talking about light cones, and that's not quite a complete description of the world. I would also like to tell you how to measure time. And you need clocks as well as light cones. And here I have a picture with some clocks. And those clocks give you the scale of the universe. For those of you who know about these things, the metric thing, that's what gives you the structure of the universe. The thing that's sometimes written GIG or GIJ or GAB or G mu nu. There's a thing with 10 components. There are 10 numbers at each point that you have to know. But 9 of those numbers tell you where the light cone is. So that's most of the information. 9 components, that's the ratios of these 10, tell you the light cone. It's the one additional scale factor which gives you the full metric. And that's given by clocks. If you didn't have clocks, you'd know the light cones. If you want the whole structure that Einstein needs for his theory, then you have to have the clocks as well. Now, what about clocks? It's very fortunate that we in nature have very, very precise clocks. These clocks come about through the two most fundamental equations of 20th century physics. One of them, of course, is Einstein's E equals mc squared. The other one is Max Planck's E equals h nu. C is a constant, the speed of light. H is another constant, that's Planck's constant. Nu is the frequency. So you see that Planck says that energy and frequency for an individual degree of freedom or something is they're in proportion. So if you have a particle, and here I imagine a particle, it could be an electron, say, that electron has a mass. That mass is equivalent to an energy by Einstein, and this energy is equivalent to a frequency by Planck. So that mass is a clock. It's an extremely precise clock whose frequency is determined by these two very basic fundamental constants. And that is basically why we have such precise clocks in nature now. Well, not in nature, people produce clocks, atomic and nuclear clocks, which ultimately depend on this kind of thing, that the rest mass of a particle, that is the particle's mass when it's at rest, which is an intrinsic feature of that particle, determines it as a clock. And this is just showing you how different clocks moving at different speeds, these are the ticks as they go, and so we have this crowding of these surfaces giving you the individual ticks to give you the additional structure that you need for the space-time. So I showed you this picture before of the light cones to give us an idea of what space-time geometry was like. If you want the rest of space-time geometry, then you need to put these little surfaces in which tell you how clocks would tick. And that is the full geometry that Einstein needs for general theory of relativity. Now, I want to distinguish these things carefully because some parts of physics don't need the ticking of the clocks. They can just get away with the light cones. And one of the most important parts of physics that does that is electromagnetism. Maxwell's famous equations, which tell you how electricity, the electric and magnetic fields interact with each other, and in fact they push each other along at the speed of light. And our light is oscillating electric and magnetic fields. Those equations of Maxwell don't need the scale factor. They just need this geometry. Now I used the word conformal before to describe the geometry, if you like, in this picture here. The conformal geometry is the geometry of angles. In space-time, the conformal geometry is the geometry of light cones. So if you are not interested in the scale factors, you're just interested in this geometry and not this geometry, then there's much of physics which is quite happy with that. And the Maxwell equations, the way photons behave, is an example. So when I say it's hard to bore a photon, it's for the good reason, if you like, that a photon well, it doesn't even intersect the first of these surfaces. It just goes zipping along, and no passage of time is registered at all on the photon. Right from if it started at the Big Bang and went off right off to infinity, it would not even notice any passage of time at all. This is also true of the other interactions, the strong and the weak interactions that describe particle forces, that the pure forces, the Yang-Mills field is called, don't notice the scale, they don't need it. It's a complicated factor that you also have masses around, and so in particle physics you do have masses, and so it complicates the situation. But as far as the basic forces are concerned, they just need the light cone structure. It's not quite true of gravity. Gravity itself does need to pay attention to mass. Well, that's, if you like, because mass is the source of gravity. But if you had no mass, then you wouldn't, electromagnetism and the other forces, apart from gravity, wouldn't be able to measure the time passage. You'd just be this geometry that you'd be concerned with. Now, that enables us to play a little trick. Remember my tricks? You could squash infinity down and you could stretch it out. Those two tricks are not just mathematical tricks. They are, in a certain sense, physically sensible. What I'm trying to say is that if you were just concerned with massless things, then you would notice this bound. It's like you don't have to be one of these angels or devils in this picture here, but you can look at the picture from the outside. As far as the massless stuff is concerned, this is just one place where there's a boundary, and you could step on the other side. So if it were a photon, then it could imagine zipping across the boundary and entering, well, what is there, you see? Unless you put something there, there's nowhere for it to go. It's a bit more direct when you think about the early universe, because in the early universe, you have the, well, perhaps I should, let's talk about the future first. Here's the remote future. Much matter collapses into black holes, which eventually evaporate away by the Hawking process. Takes around a googol years or so. Mainly photons left, and the photons don't experience the passage of time. There might be some things like electrons running around. And then here's a little problem I have with the scheme. So I propose that in the very, very, very remote future, even much longer than this time here, mass starts to fade out. And so the electrons begin to become massless. There's a sort of opposite to a Higgs process, where in the very early universe, you know that things like that mass gets acquired by particles. And then again, the idea is in the very remote future, mass fades away again. So I'm introducing that hypothesis here. And with only massless ingredients left, there's no way to build a clock. Eternity is as nothing for a massless particle, and therefore the right geometry for what's left in the universe is this conformal geometry where big and small are equivalent. Now, you see, again, is this just a mathematical trick? Well, remember we had our mathematical trick already for well, actually I haven't quite said it yet, which I have to find it. Here we are. Here is the Paul Todd's trick. It's just really the other end of this transparency now. Paul Todd introduced with this elegant mathematical proposal that the space-time to be extended conformally as a light cone structure, that is, to before the Big Bang. So the thing is that this is again a mathematical trick, if you like, which is expressing the way that the universe was special in the Big Bang, but it's also perhaps saying something physical, because we have got to believe with these new experiments of the LHC and so on, and theory before it, that when you have very, very massive, when you have a very, very high temperature, as there would have been in the early universe, then particles were effectively massless. If you like, when the temperature gets higher than that which creates Higgs particles, then then you have no mass left, and everything behaves as massless particles. So, if you like, it's not so much just a mathematical trick. There are these particles which don't really notice this beginning. And if they came from somewhere, where did they come from? Well, that's the idea. You're trying to combine these two mathematical tricks, and I hope I can do it on the same picture there. The remote future of one eon becomes the Big Bang of the next. And since there's no mass around at that phase, that's a perfectly sensible physical thing that you can describe. Okay, now of course you can boggle at that if you like, and I think most people probably do, with good reason, because it's an unfamiliar idea. And often people say, well, isn't the Big Bang enormously hot and enormously concentrated and enormously compressed and dense? Whereas the remote future is the complete opposite, enormously cold, very undense, everything all spread out. Well, yes, but this is exactly what happens when you do the conformal trick. You squash the space in, temperatures go up until they match the high temperature that you would have had in the Big Bang. So as far as the local physics is concerned, if there's no rest mass, it makes a lot of sense. Nevertheless, you have to worry about whether it's real or not. That is nevertheless the idea. Now, I just want to say a couple of things, and then I want to say something about, is it true? Well, is it true? We need to know, are there observational consequences? And are those observational consequences satisfied or not? But before coming to that, let me address one point which might worry you with good reason. I started off talking about the second law of thermodynamics, and you say, well, how can that make sense in a cyclic universe? And indeed, people used to worry about that with these collapsing and bouncing universes. You might say, how do you have an entropy which can keep on going up and up and up, even though the universe seems to be the same all the time? That problem came up with a steady state model, but that was dealt with in the particular way that the matter appeared. But here, you have this issue. How does the second law work? If it's increasing all the time, so in the pictures that I was just showing you with the eons, you see, you might say, how is it that the eons, as they keep going, can have an entropy increasing all the time and yet be consistent? Well, the argument that I make is the following one, and it depends upon the Hawking evaporation of black holes. I did say earlier that the biggest entropy by far in the universe now is in black holes. So that's the key thing you have to deal with. Now, according to Hawking, and I accept all this, the black holes ultimately disappear. But what happens then? Well, you see, there's been a lot of argument amongst physicists about this. And Hawking originally, I'm going to call this the young Hawking, sometimes you can think of it as the old, well, I mean the young Hawking, that is in 1976, said that information got lost in black hole singularities. I think he was right. However, later on in 2004, he changed his mind and said, no, somehow that information gets out again. Now, I think he was right to begin with. I don't want to go into these arguments, but it is a sort of controversy that you find between physicists. I think the original argument was very clear that information is lost. What that really means is that degrees of freedom get lost, and if you go back and look at what the entropy means, and I'm not really going to this here, but you find that the zero of that entropy has to be reset. It's a subtle point, rather, that the black hole, if you like, takes away lots of degrees of freedom, and that somehow redefines your entropy. There's never a violation of the second law of thermodynamics. The entropy keeps going up. But at a certain stage, you say, whoops, I've got the wrong definition. I shouldn't really have included all those degrees of freedom which got swallowed by the black holes. Let's start again and use a different definition. It's fine. It's completely consistent with the second law, and it makes a picture which is consistent. But it's a strange idea. But when you have black holes disappearing, strange things happen, and this is one of them. So the idea is that the black holes eventually evaporate away. They lose their degrees of freedom, and these no longer contribute to the usable entropy that you calculate, and so you change your mind about what you mean by the entropy. The zero of entropy is reset. The second law, in a sense, is transcended. It's never violated. So it does make sense. Okay, that's the idea. Now I want to talk about the observations. First of all, what is the biggest observational effect that one could conceive of? Well, the biggest effect I could think of. I tried to think of, is there any way in which a signal could get across from the eon before us to our eon? Now, you see, it has to get through this extremely hot and dense situation where the let's go to our pictures here. We have the remote future, and somehow you might have photons or something going on. And the argument is that they actually can get through to the other side. Well, I can't think of anything using photons which would be big enough, but there is something. I did mention about the black holes in our center, the center of our galaxy and other galaxies. Ours is a pretty big one, 4 million times the mass of the sun, but by standards of galaxies around, it's not that huge. We are on a collision course with the Andromeda galaxy. It won't hit us. We won't hit each other very soon. None of us will be around by then, but it's only a few thousand million years, not terribly long. And we will collide with the Andromeda galaxy. When we collide, our black holes, well, they might just miss, go through each other. Lots of stars will miss, and we might just go through. Then we'll come to a halt and then come back again, and there'll be another collision. One of these times, if it's not the next time, one time it will happen. The black holes will not head-on collision, but they will capture each other, spiral around each other, lose energy in gravitational waves, and swallow each other up with an absolutely stupendous explosion. What you have to think of as the well, our galactic black hole is 4 million solar masses. Andromeda one is a bit bigger, a lot bigger probably. You have to think of a few percent of that total mass almost at once converted into energy. So that's an absolutely stupendous explosion. It will be mainly in the form of gravitational waves. That's ripples in space. And that's not very, it wouldn't probably, I don't know whether it would hurt the people living on the planet when that happens. I don't know. But that's not the point here. I have a space-time picture of the sort of thing that's happening. This is now in the previous eon. I'm not talking about us and Andromeda. I'm talking about similar things that might happen in the eon prior to ours. This surface here is the crossover between the previous eon and our eon. This is us up here looking back with our light rays along this past light cone to the microwave background radiation, which is just above the crossover surface here. And this explosion, when these two black holes collide, a huge explosion in the form of ripples in space-time, that's gravitational waves. Then they hit this surface here, and now you have to go into the mathematics. What it does is it gives a kick to the initial dark matter. Now you see, I talked about the cosmological constant. That's often called dark energy. I don't like the term, but that's what it's often called. And it's called a great mystery why it's around. All I can say is that you definitely need it for this scheme. If it weren't there, the scheme would not work. The other thing that needs to be there, and people call a big mystery, is dark matter. Dark matter is actual material of some sort, which doesn't, you can't see it. However, it does influence other things gravitationally. And on this scheme, it has to be created afresh every time you go from eon to eon. So in order to prevent it building up, you need it to sort of be gradually decaying through the history of the eon, and then it's created again. So that's the kind of thing that happens in this model. So there will be dark matter created here, just after the crossover, and this gravitational wave will give it a kick. It'll give it a kick, an impulse in the direction of the wave out here, and that impulse will give it slightly motion. Well, it depends on, see here we have one of these kicks a long way away from us, and then the kick will be in our direction, and so the motion will be in our direction and look a little warmer. What you would see would be a circle in the sky, which is slightly warmer. If it's inside, like this one here, then the kick will be away from us, and so it will look a little cooler. I have a picture here which is to give you some sort of feeling for what it's like. Again, you have to think of these as circles, so squash it back again if you will. And here we have lots and lots of ripples. This is really meant to be ripples in a pond as an analogy. So imagine you've got a pond, it's been raining, every drop of rain causes a ripple which comes up. Stops raining, you look at the pond, looks just like a lot of ripples. How do you know that that's made up of individual impacts from raindrops? Well, you've got to do some clever statistics. Nevertheless, you could, in principle, decide that. Question here is something similar happening? In the microwave background, do you see things like this with ripples? And that is the question that I want to address here. here I have, in a sense, we're seeing through, if this is true, to this events with supermassive black holes. Now, there's two ways people have been looking at that. This was an Armenian colleague of mine who had some ideas about this to detect when where these rings were. I've drawn them rather faint deliberately here because they're rather hard to see. There was a point about them is that they tend to be concentric sets, because you might have a cluster of galaxies, and this happens once, and then it happens again, and these would look like circles with the same center. That's one possible diagnostic. It may be you're just interested in the ripples themselves, and can you somehow detect the signal, the kind of circular region that would be of an impact, a kind of wave coming towards you or away from you, and that's the kind of thing. Okay, well, I want to show you some pictures, but just before doing that, let me show you one of the tests. This was the test that Vahe Gerzajan and I, my Armenian colleague, and I looked at. So you want to see, are these things that you see in the sky real or not? So you might say, well, look, I see these circles. And then somebody else comes along, well, you don't. Those circles are just pure randomness, and they would be there without any of these mechanisms. And it's often hard to persuade people that what you're seeing is a genuine effect or not. And we eventually were led to the following thing, which I'm calling a sky twist test. And I'll just describe this in a minute because I want to show you some pictures. You have, first of all, you look in the real sky and see whether you can see these circles. Well, the actual test he was looking at was not quite the thing I'd originally thought of, but you look to see whether the temperature around the ring is a little more uniform than usual, which is called low variance. And that would be a way of distinguishing one of these ripples from the background. So that was his idea. Look for low variance circles, and the signal is not very clear, but to make it clearer, what you do is to see whether these come in concentric sets, and are these random things in the sky, or are they really there? And to see whether they might be really there, we try, first of all, you look for them in the real sky, and then you look for them in a twisted sky. So you take the sky, twist it like that, and look for circles in the twisted sky. And that means in the real sky, you're looking for elliptical shapes. And then you look for slightly more twisted, so you're looking for things which are more and more elliptical. And do the numbers that you see reduce when you increase the ellipticity? And there's a thing called S, and S, when our thing starts at 0, that's no twist, 2, 5, 10, and goes up to 80. And these numbers here refer to the ellipticity. So when S is 2, you're looking at only, this is the ratio of the minus the major axis of the ellipse. Here it's only about 1 or 2%, different from an actual circle. And this goes right down to here where you're looking for S equals 80. You're looking at about 2 to 1, so ellipses which look like that. The ones up at the top you simply wouldn't see as ellipses. They just look like circles to the eye. Nevertheless, they're not quite circles. Okay, well, can we have the pictures? Is there somebody up there? I have to see what's going on. Can we have the first pictures, please?
Just one moment.
Ah, good, thank you. Yes. Now, I would, I suppose, have to use a laser pointer or something. Not that I'm very good with these things. Look at the top picture. The top picture up there, these are the centers we find, and those over here are the actual circles where we're looking for low variance circles where you see at least 3 with the same center. So that's the device. In order to make it more significant, we look for concentric sets. The individual circles, it's a bit hard to tell whether they're really there or not in the way we do it. So there you see there are 352. I should say the strip taken out of the middle is where the galaxy is, and we like to blot that out so you don't actually count circles whose centers lie in this forbidden strip. However, we do count semicircles, or a little bit more than semicircles, if the center is outside that region. And if they look, I don't know if you can see the colors, the red ones are the warmer ones, so according to the theory, they'd be the more distant ones where the signal is coming in our direction, and the bluish ones are the closer ones, which the signal is moving away from us. They're the cooler ones. And Now we start to twist. So this is the actual sky up here. We see 352 centers. Now we twist, so it's about 1 or 2% away from a pure circle. And you notice the numbers drop by more than the factor of 3. So it seems to be sensitive to the circularity. Can we move up the picture, please? That's it. And we increase the ellipticity, and the numbers go down and down, up a bit more, until with this, finally, when S is 80 at the bottom, you can actually start to see the ellipticity here. It's sort of, those ones there, you see. They're about 2 to 1 ellipses. And there you find the numbers drop to about 15 or so. That's the kind of number which probably don't mean anything. They're probably just random. Okay, can we have the next one, please? Okay, now this is looking for, fine, thank you. Looking now for centers of 4 circles. So each point over here, now they're colored to give you you probably can't see them too well. These are sort of reddish. And you see for each center of at least 4 of these low variance circles, that's marked down here. And we see 56 of them still. Now, a curious thing about this is how crowded they are. You notice that there's certain regions where they're very, very crowded. There's a sort of hot spot there, and there's a kind of cold spot over there, and then there's other regions down there, which I'll come to shortly. But you do see a very, very inhomogeneous distribution of these things, which is very curious. I was not expecting that at all. I thought, well, the universe is probably going to look pretty uniform, or the previous eon, where it seems to be pretty irregular, at least with respect to these signals. It means there are certain regions where there are lots and lots of really massive black holes which tend to run into each other. In other regions, the black holes are not so massive. Maybe they're a little more dispersed around and so on. And so you don't see these collisions so much. Well, I don't know, but at least you can account for it even if it's not expected. Now let's twist the sky. And this is, first of all, this twist. You notice they drop now by a factor of 4 or so with a little tiny twist right down. They start to disappear altogether. Even here, they've gone. Can we go right up? You see, this is the 2 to 1 ellipses. There aren't any. So you simply don't see them when you're looking for ellipses of significant ellipticity. They're just gone. And so there is something in this signal which depends upon them being circular. And that is very much what the theory says you should find is circular shapes, not elliptical ones. I don't know how you'd produce elliptical ones. So that's consistent with the scheme. Can I have the next one, please? Now, I should explain, this was stuff that we did with this again is the same thing. Yeah, sorry. This is now exactly the same with the 3 circles, but this is the South Pole. It's rather extraordinary that there's lots and lots going on in the South Pole region. When I say the South Pole, that's below the galactic disk. It means not our south, but this is the North region now, and there are far fewer in the North. Very strange, why there should be so many more on one galactic hemisphere from the other, but that seems to be what we see. That's the South Pole, and then go back and we'll have a look at the North Pole. Well, with the South Pole, you see there are very, I'm doing it, am I? Yes, I am. Oh, I didn't know that. Isn't that clever? I didn't know I was that clever. Down at the bottom, you see this very, very crowded region. Now, colleagues here in Warsaw, Paweł Nierowski, Christoph Meisner, and now some analysis being done by Daniel Ann, and I'm going to show you their results in a minute. They have a completely different way of looking for the signal. So you don't necessarily expect to see a detailed correspondence with these things, but I want to show you the things that they find. Here, I just want to point out there are certain regions here of, for example, very, very crowded regions of the red ones. That means very distant, according to the theory, and the blue ones a little bit below. If I can find that again down here. So it's sort of red over here and a little down this side, the blue ones, which means the cold region here and a warm region, or at least warm circles, not necessarily warm overall. Okay, can we have the next picture, please? Now let's see if we can get this one to work. Now they've looked at this is just saying you what they're doing, actually. They look at rings next to each other, where they're looking at the average temperature. The inner ring temperature is compared with the outer ring. And if they find a big jump between the two, that's a sort of cliff, if you like, in the temperature. You imagine a cliff, and the sharp edge is what they measure. Now let's see the next picture, if I can get it to do this. That's it. Now these rings, there are lots of pictures here, and they just basically depend on how thick the ring is they're looking at. And I think that's up at the top somewhere. The epsilon thing in the corner up there. Oops, no. Let me concentrate on a particular one. Where, here, look at that. They're extremely crowded. This is for a particular width of ring, and you see a lot of red ones altogether. And that very much corresponds to the region I showed you before in our picture, the South Pole picture, where you find a great deal of concentration of rings which come towards us. There's also a separate point here. The point is that it's like a wave coming towards us with a big leading edge and a tailing off in the back. Because to see red here, you're seeing the up cliff. Whereas the blue ones, you're seeing a down cliff. And you don't see the back of it. Why don't you see the back of it? Because it comes up very gently. And this means that the impulse you're looking at has a big sharp edge and it tails off. And that's the sort of thing you would expect from the theory. And I find it rather striking that we do indeed, this is not us, this is the Polish people who've been doing these observations, or doing this analysis here in Warsaw, and with the Korean fellow who's helping them do the computer work. And they, quite independently of us, seem to see this incredibly crowding, regions which seem to be these effects are very large, and other effects, particularly in the northern hemisphere, where you see very little. What's going on? Well, you see, conventional theory is that these irregularities in the microwave background come about from quantum fluctuations, which should be very random over the whole sky, expanded out by this exponential inflationary expansion. So that is the standard view. However, I have no idea how within the standard view you could produce this enormous irregularity that you seem to see here. So it does seem to be something which is giving some kind of a boost to the kind of idea which I've been describing here. So far, these are very, very new. I only learnt about these just this past week. So these are pictures that they just made just this last week. So it's really up to date, what I'm showing you. I have to wait until how other people explain them. Sometimes say, well, you shouldn't trust this is, I should say, the Planck data. This is the satellite, which information has just recently been released. And some people say, well, the things are all photoshopped anyway, you shouldn't trust it. And this is just somebody's rubber who's just gone swiggling around like that. And say, well, you can believe that if you like. I hope that's not what's going on. But anyway, we're left with something to think about. And I'll leave that with you as something to think about. Thank you very much indeed.